Good morning, everyone. Welcome to the seventh annual symposium of the Center for Automated and Transformative Transportation Systems. My name is Beher Abdulhai. I am a professor at the University of Toronto and the co-director of CATS, jointly with Professor Amer Shalabi. If you are, before we start, let's first start with land acknowledgement. We wish to acknowledge the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron, Wendat, the Seneca, and most recently the Mississaugas of the Credit River. Today, this meeting takes place. This meeting place is still the home to many Indigenous people from across the Turtle Island, and we at the University of Toronto are grateful to have the opportunity to work on this land. If you are new to CATS, I'll just give a very brief introduction to kind of set the stage. And if you've been with us from the previous years, then you're probably very familiar with what we do. So the CATS was established at the University of Toronto in 2017 and operated since then as a partnership, mainly led by the Faculty of Applied Science and Engineering at the University of Toronto, at the Department of Civil and Mineral Engineering, and working in partnership with the City of Toronto, the Region of York, and also with funding from the federal government from INSERC. So what is CATS exactly, and what is transformative transportation? I don't think there is a textbook for definition for what is transformative transportation, but you can think of it one definition, you can think of it as such. It is like we have a new transportation system that is emerging very rapidly from a swell of innovations, market-driven innovations, not only in technology, but also in the way transportation services are provided to the public. And society organizes usually around the new technologies, and governments try to regulate the spread of the technology and the impact of technology and so on. But obviously, the elephants in the room are the so-called the ACEs, which are automated and connected vehicles, electric vehicles, and shared mobility. So in CATS, we try to ask the key questions because we don't want to speculate. Like, for instance, you hear speculations that automation would increase demand and increase urban sprawl. Others would say, no, it will increase capacity of the infrastructure and hence it will help congestion and so on. So there are positive and negative speculations about what would the ultimate impact be of these new technologies. So in CATS, we try to take an academic approach to this, where we identify the key questions and then analyze demand and supply. Is demand going up? Is supply performing better, or is it the opposite, that demand will go down? And perhaps the capacities of the roads will also go down because adaptive cruise control, for instance, leaves quite a bit of space in front of cars, and therefore there will be a deterioration. So we have to analyze what the true impacts are on demand and supply and system performance, quantify the effects in numbers. So is it 20% improvement, 40% improvement, or the opposite? And then predict future scenarios, how cities will evolve around those technologies, and come up with evidence-based research that informs policy So policy would be based on rigorous analysis and quantitative numbers. And we also try to create control systems to manage the infrastructure in the presence of those technologies in order to optimize the future system. So this is pretty much our mission. You can think of it as three themes. Theme number one is quantifying transformation, meaning that what will be the impact of those technologies and service provisioning on the system if we just watch it grow. So if we just let like people buy autonomous vehicles and whatnot, then how the system would evolve and what would be the quantitative impacts of those technologies. But at the same time, if the transformations are going in the wrong direction, for instance, people are becoming more dependent on cars, congestion is increasing, and so on, then we need to think about what can we do, like interfere in the system operation and management. What can we do in order to steer the transformation in a positive direction? And positive means sustainability, meaning the triple bottom line sustainability, economic, environmental, and social sustainability. So whatever we do, we want to make sure that we're helping the economy, we're helping society, we are helping the environment. So as I mentioned, quantifying the impact that involves quantifying demand changes for passengers, quantifying demand changes for freight, and quantifying system and infrastructure performance changes. And then enabling positive transformation is coming up with policies and systems, control systems, and management systems to harness the technology in a positive way. That includes, for instance, exploiting the benefits of automation, exploiting the benefits of artificial intelligence, and then exploiting the benefits of new service provisioning methods such as, for instance, mobility as a service and transportation as a service, exploit the possibility of e-sharing, sharing vehicles and sharing rides, and greener technology with the goal of having zero carbon. So this is pretty much an intro to what we do. The professors involved in this are Professor Amer Shalabi and myself. Amer is a transit expert. Myself, I operate in traffic control and management. And then Professor Eric Miller and Professor Kandekar Habib, both of them are in transportation planning and demand analysis, so the demand side of transportation. And then Professor Marianne Hatsupolo, she is the environmental expert in our group, and Professor Matthew Roorda, it's freight and logistics. And then we also have two staff members, Dr. Karim Osman, who is a postdoctoral fellow, and Dr. Toka Mohammed, who is a research associate. So this is just a quick overview of who we are. I'll stop there and need to stop sharing. And then today we have a full day ahead of us. We'll start with a session on traffic AI in the morning, and then we'll take a break at 10:45, and then we'll go to another session on behavioral modeling in the context of emerging mobility. Then we'll have a lunch break, and then we'll have a guest speaker from the City of Toronto, Mr. Roger Brown, will talk to us about transportation challenges in Toronto and the way forward. And then we'll finish the day with a session on innovations in freight, logistics, and air quality modeling. So with that, we can start the traffic AI session, artificial intelligence. And the first presenter will be Dr. Xiaoyu Wang. Xiaoyu, are you present?
Yes, yes.
Okay. So just a brief introduction. Dr. Xiaoyu Wang is a postdoctoral fellow um, in the Department of Civil and Mineral Engineering at the University of Toronto. He received his PhD in civil engineering from U of T, and he worked with me and another professor, Professor Scott Saner from Mechanical and Industrial Engineering. His research interests include control, reinforcement learning from artificial intelligence, and the applications of control and reinforcement learning to intelligent transportation systems and multi-agent systems. And on the personal side, Xiaoyu likes biking as his hobby. So, Xiaoyu, I turn it over to you.
Thank you.
You have 15 minutes to present and 5 minutes for Q&A. So please
Yes.
go ahead.
Thank you, Professor, for the brief introduction. Let me share my screen. Everybody can see the screen, right?
Yeah,
So it's a thrill to do the presentation in the first place of the day. Hello, everyone. I'm Xiaoyu Wang. I'm excited to share our research products in this topic, eMartin, where we try to address partial observability issues in uh, adaptive traffic signal control problems. And special thanks to the collaborators, Eyal Tetler, Ilyas Smirnov, and Professor Scott Saner and Professor Bahir Abdelhai. So, wait. Okay. We need adaptive traffic signal control. That this topic should be like widely known by many of the audience, I guess. Mainly, the main focus of this topic is to address the traffic congestions happened mostly in the urban area or the highway, uh, which causes like productivity loss, fuel wastage, and pollution. But traffic signal control itself is it's not a like brand new topic. It has been developed for more than half a century. For example, in early 20th century, we have fixed time control where researchers were engineers, go to the field, take flow counts, and develop the timing plans for each of the intersection and each of the traffic signal lights, manually. Then in the middle of 20th century, we have some idea of actuated control where people will place like inductive loop detectors uh, under the pavement. Then when there's a vehicle driving through it, we have an idea. So with these sensors, we can extend the green light of a specific direction. For example, in a in an intersection, you have major road and minor road. And if you can detect, you can sense that there are too much vehicle flowing through the major corridor, you can opt to extend this major movement to give a better throughput. And later in 20th century, we have something called adaptive TSC. By saying adaptive, it means moving from actuated control. We're more active in aggregating real-time data, and we're more active in like modifying the timing plan in real time. It's not only saying like if there's a vehicle, we extend another 35 seconds. We would rather like craft the whole timing plan based on the real time or uh, the in-field aggregated data. It could be flow, it could be whatever else. But at the end of 20th century, we sometimes call it most of the methods developed in late 20th century, they focus on cycle level control. They basically do the decisions on time splits. So if we glance back of the history development of TSC or ATSC, we can see as we have more concrete sensor, we have more plentiful data, then we can apply better and finer control schemes over the intersections. But till today, there are many people, my friends, my colleagues come to me. They heard that I'm doing traffic research, and they just ask me, why am I experiencing that? Sometimes I'm driving towards an intersection, and seems like I'm the only person, I'm the only vehicle in this intersection, but I still got I still got a red light. They will start complaining like, what are these traffic guys doing? Are they doing something wrong? So based on this question, we will see another more concrete example why this is hard to resolve. But as a route choice, today we're pursuing on having more than second level adaptive control solutions. For example, if you have cycle level adaptive control, it is hard to make individual vehicles satisfied because in which you're optimizing over like traffic flows. So that's why we need even more fine data, even more finer control. So ideally, if we say we're controlling a corridor, a corridor, um, or even a network, an ideal approach is to have an Oracle centralized agents, which observes globally, optimizes the target subnetwork globally. But the downside is that it's intractable. It's too complicated. So from the learning perspective, we can have multi-agent collaboration at which we developed a method called eMartin, the basic eMartin. Um, we when we are controlling either corridor or network, we have set of agents which each controls an individual intersection, but they're not independent. Each of the intersections will collaborate with its close neighbor. So the agent will first compress the raw observations with the eMartin encoder. Then these EI, we call it embeddings, will be broadcasted to the immediate neighbors, and uh, the neighbors will aggregate all these abstracted information, which is an abstraction of the raw observations of each agents. And after aggregation over the neighborhood, the agent I will make a decision based on this joint abstracted observation. It saves us like computational complexity. It also saves us the communication complexity. Uh, However, this is not the final answer of ATIC in second level, and I will quickly show you why. So a big topic is the limited traffic data accessibility, and mathematically we call it partial observability. So notice that here I'm using the term of raw observations. It's not the raw states. It's not the traffic states. What we observe is less than the states. Why would that happen? Here's an example. Still two intersections, very simplified scenario. And we have surveillance cameras in front of each approach. And this vehicle is driving on this corridor. So there's a type 1 lack of sensing. When you have a surveillance camera, It can only faithfully tell you the information within the detection area. That means all of that detection area labeled by this purple shade, the vehicles will not be sensed. Then we have a limited sensor coverage on the in the traffic network. So this vehicle keeps moving forward and joining the detection area of intersection B. Then there's a second type of lack of sensing. It means it says we have only a snapshot of the real world. We have there's a lack of dynamical properties because in the surveillance camera, you can use modern like computer vision technologies to capture the position of the vehicle. But what about acceleration rate and whatever else? If the pedal is pushed down, all those dynamical properties you can only estimate from the videos or from the differences in between frames of the videos. You cannot get a precise uh, traffic states in this sense. So with those two types of lack of sensing in our mind, let's take a look on this scenario where you have a platoon of three vehicle coming eastbound and a single vehicle coming northbound. And currently, the intersection B uh, this should be eastbound green, not northbound green. But anyways, it's idling because no vehicle is in its detection area. But in intersection A sees the platoon and allows it pass through because this is the only movement there's are vehicles. 17 seconds later, this vehicle approaches the stall bar, and intersection B says there's no eastbound vehicle in A and B both. In both intersections, both detected covered areas, there's no vehicle at all. So maybe I should allow the northbound vehicle pass through first. But to be noticed, once this intersection changed the phase, it will suffer from a blackout period because the traffic light will go through the yellow phase, the all right time, and serve the minimum northbound green time, which usually determined by the intersection layout. But as C is not able to see in the three vehicles, it allows the northbound vehicle going through. But 8 seconds later, it starts holding the eastbound platoon. There's a grid delay will be induced because the blackout period. So we don't want the agent to make these kind of not intelligent enough and not wise enough decisions. What can we do? In this t equals 17 second, what else can the intersection uh, be aware of rather than the role observation, which is the like video readings? Is there a hint of the existence of this platoon? Luckily, the answer is yes, because if you recall, date like 10 seconds back, this platoon was released by the intersection A. So it was exist in the history of the sensing from intersection A. So intuitively, we would say history matters. We can augment the agent's input with short history of the observations. And this is not a tutorial of uh, reinforcement learning and Markov decision processes. So we just call that mathematically uh, there was a non-Markov issue in this case, and including the history will compensate for that. It will alleviate the problems caused by this non-Markov property. The history of observations in each agent and the executor of the E-Martin architecture stays the same. What about the complexity of data input? For example, you have 20 seconds put into the history, then your input space is exploding. So in order to handle the sequential data efficiently, we introduce the transformers, which is a cornerstone, which is the backbone of modern like generative AI technologies. You everybody most people use the ChatGPT or whatever large language model, and Transformer is exactly the backbone of those uh, models. However, reinforcement learning is sensitive to neural network architectures, and Transformer, on the other hand, suffers from large memory footprints and high latency. So in our research, I'll just keep these mathematical introductions. So in our research, we put the transformer block into the eMarlin encoder module. And beyond that, we do need some other like better practices, which enables the eMarlin to work well with eMarlin, because we need to address the two adaptive issues we previously mentioned. So in terms of implementation practices, in this work, we're using the canonical transformer block, which is the like most classic one. And we noticed that with the proper selection on the model size, um, the canonical transformer block can actually stabilize the training. It can avoid the issue mentioned before, like the large footprint requirement and the unstable learning between when transformer and reinforcement learning happens together. And secondly, we noticed that in our case, the sequence alignment is important because you want to have a semantic meaning of the sequences. And in our case, the current time slice is the most important ones. And when you're dating the current slice back to like horizon of H, you want to align each of the sequences to the current slice, which tells the agent that uh, you should really focus on which frame in this sequence. And thirdly, we need to do the padding and masking properly, because if you don't mask out like uh, void void slices, those zeros actually has meaning in traffic states. For example, it could mean there's like no vehicles, there's no the vehicles stopped, no speed, this and that. So you can't just let those padding slices going through the whole eMarlin architecture. Why do we need to having the PO partial observability being addressed? The benefit is that with the PO being addressed, we can develop a sensor agnostic architecture. This whole solution it can be adopted to any sensor schemes you have in your mind. For example, in the finite screen, we have discrete traffic state encoding, where you exactly know the position and the speed, normalized speed of each individual vehicle. To be more coarse, you can have vehicle count and queue count. It's less precise, but still you know there are how many vehicles. What if you what if we only have like loop detectors? We can have a group of loop detectors on stop in front of the stop bar and several hundred meters they pushing upstream. We can even deal with that. The eMarlin X or the eMarlin transformer architecture can still deal with that kind of sensing schemes. So how can we show that eMarlin X is this powerful? We do experiments in the Northwark region, where the central intersection is the Young-Stills intersection, and we focus on controlling the 5 intersections along the Young corridor. And we strictly adhere to the FHW in NEMA scheme. We don't allow although we're doing like second level adaptive control, we strictly adhere the policy constraints. Yeah, this is what we call constrained variable phasing scheme developed according to the NEMA scheme. And regarding the reward, we're counting the queue length. which is equivalent to the stop time. Empirical results, we have a pre-timed baseline and several other reinforcement learning baselines. And you can see even from eMarlin to eMarlin LSTM to Transformer, we can earn significant improvements. And what else? What about addressing the PO issue? Here we present the results where each of the agents are using a specific detection scheme. And this is in kind of Oracle, this one in blue, sorry, in green. So it gets the best performance labeled as Oracle. But you can see, even though we have other sensing schemes, whenever you introduce the transformer and also the eMarlin Plus architecture, it can actually getting much more closer to the Oracle performance compared to the other reinforcement learning baselines. So the future of eMarlin X, we're collaborating with the City of Toronto and the TDC to try to try to deploy in 4 intersections in the Don Mills area in front of the Faribault Mall. And the infield test timeline is targeting on having it infield in early 2025. And that's all for today. Thank you for your patience. Feel free to ask questions.
Thank you very much, Xiaoyu. Anyone who wishes to ask questions? Okay, I'm also looking at the chat box. There are no questions. So with that, we conclude this presentation. Thank you, Xiaoyu.
Thank you
And
all
we'll move
for
on to the
your patience.
next. So Xiaoyu talked about traffic signal control at intersections. The next presenter is Dr. Omar Al-Samadisi, who is a postdoctoral fellow in the Department of Civil and Mineral Engineering at U of T, working under my supervision. He also finished his PhD at U of T, addressing freeway control. So his research interests are in ITS in general, and with a particular emphasis or focus on, again, AI, artificial intelligence and reinforcement learning based optimization. His current work aims to optimize freeway traffic flow, both macroscopically and microscopically. Before his PhD at the University of Toronto, he had his bachelor and master's in wireless communication systems and electronics and communication engineering from the Arab Academy of Science and Technology and Maritime in Alexandria. So Omar, please go ahead and start sharing your screen.
Let me share my screen. So good morning, everyone. Thanks, Professor Bell, for the introduction. So today I will talk about freeway control case study on the QEW. This work was done by me and in collaboration with Xiaoyu Wang and under the supervision of Professor Abdel Hai. So first of all, as a main motivation for conducting this study is congestion, and congestion on freeways is a worldwide problem. Congestion is costing economy here in GTHA up to $11 billion as stated by MTO in 2021. And Toronto won the 7th worst city in the worldwide for congestion in 2023. So benefits of freeway controllers are well established in literature for one or few congested on-ramps. However, for along heavily congested urban freeways like QEW or 401, resolving one bottleneck only fits to the next. So we need to do comprehensive analysis and we need to control a new design for a controller is required to control such a freeway. First of all, let's talk about the source of congestion on a freeway. And problem is a bottleneck, and a bottleneck is a location where the flow capacity upstream to this point is higher than the flow capacity downstream. And whenever the arriving demand from upstream is higher than the capacity downstream, um, congestion is triggered, and we have two negative effects. First of all, is capacity drop. So the output flow from this bottleneck is lower than the lower flow, which is the capacity of the lower neck, the bottleneck, and blocking of off ramps. So when congestion vehicles start queuing, congestion start growing upstream, blocking off ramps. So vehicles that wants to exit the freeway keeps waiting and increase the congestion and the travel time for everyone. So solution for that is to use controllers to limit the flow entering a bottleneck location to the bottleneck capacity. This can be applied by RAM metering, by controlling the flow entering from the on-ramp, or variable speed limit by limiting the flow entering from upstream. Here is some videos to illustrate difference between controlled and uncontrolled. So here is the uncontrolled scenario where vehicles are fighting to merge and go to the freeway. And then we can see here RAM metering applied. You can see how we can limit the flow coming from the ramp and increase the flow exiting the bottleneck. Then when we apply variable speed limit, we can see clearly that we can limit the flow coming from the upstream and leave the on-ramp uncontrolled, and which also maximize the flow exiting the bottleneck. So we implemented regulator approach with which is a simple rule-based controller. So we control the vehicles entering from the on-ramp based on this simple rule by setting uh, a goal density or occupancy where capacity happens. So when we exceed this density here on x-axis, we limit the flow so to go back and maximize the flow. And when we under this under capacity, we can push more vehicles so that we maximize the flow at the bottleneck. Also, there is the same rule integral regulator for variable speed limit. So controls the speed upstream based on the same rule, and we set the same goal or density goal for the controller. So when we apply both together, we apply first RAM metering, and then variable speed limit is applied whenever a linear or RAM metering fails to resolve congestion. All controllers are implemented using MSN APIs. And also we implemented reinforcement learning controller, and reinforcement learning is just an agent that applies action to an environment and then receives the new state in this environment and a reward based on how good is this action. So it keeps repeating that and training until it learns how to optimize a certain goal, just like how we human being learn to do a task, like a baby learning to walk. So when we try to implement reinforcement learning or design controller using reinforcement learning, the agent is either variable speed limit or RAM metering. The environment is the network, traffic network, MSIN simulated network. We have the state is the real traffic info at the bottleneck. The action is either the ramp flow or the section speed limit or both of them if we want to apply both. The reward is simply the output flow from the bottleneck, which reflects the total travel time. If we maximize the output flow at the bottleneck and try to get more vehicles out, is equivalent to minimizing total travel time at this bottleneck location. So we applied these controllers, both reinforcement learning and regulator-based controllers, on several test beds. First one is hypothetical network from literature. This is very popular networking literature. And Weston Churchill on-ramp from QEW with excessive demand, very high demand. And then we have a full eastbound QEW network with 26 on-ramps with calibrated real demand. So we have calibrated this network and applied the controller on it. We have summary for results for each network. First is the literature network. We have here we can see the first column is the regulator's results, and the second column is the reinforcement learning results. So this is the network and the demand applied. We have 3,500 from mainstream and 1,000 vehicles per hour from the RAM. Given that demand to a two-lane freeway, so we are slightly exceeding capacity. So without control, we have congestion, but when we control, we can avoid this congestion and get benefit in the range of 50% for RAM metering and 40 something percent for high speed limit. But we can see clearly that here reinforcement learning controllers beats regulator, and also any controller is better than none. Applying any kind of control is better than leaving the freeway uncontrolled. And we can see here we split the benefit between the mainstream and the on-ramp. We can see that RAM metering sometimes adds some delays to RAM travelers when we apply the regulator. However, when we apply reinforcement learning, we can fairly distribute more the benefits between both travelers, mainstream and on-ramp. So all are benefiting. When we go to tertiary network with excessive demand, we can see here that we have 3-lane freeway, not 2 lanes, and we have 6,000 vehicles coming from the mainstream, which is almost at capacity without adding any ramp flow. So we can see clearly that we have critically high demand. In this case, we can find that very speed limit, playing with mainstream or applying any very speed limit here, is not very effective. We can also only get 0.3%, or maximum using reinforcement learning, we get 3% decrease in total travel time, while RAM metering is still effective when we apply it to such highly congested scenario. So RAM metering can get benefits still in the range of 44-45% decrease in total travel time. We can learn from here that at very high congestion, very speed limit might not be very effective. So we take these results and apply it to the QEW network. We can see clearly here for the full network starting from Hamilton till Gardner Expressway, applying RAM metering gets us about 14-15% when RAM metering or coordinated RAM metering are applied, while very speed limit is only 3.25%. When we look at the heat maps, we can see clearly that very speed limit is not very effective. It's only 3%. And when we looked into the reasons behind that, we find that the back-to-back RAM feeding to the freeway more vehicles is very challenging condition to apply very speed limit, because very speed limit needs space. When we apply it to isolated RAMs, it's very easy because we don't have limitation on how vehicles queue on the freeway. But here on such high dense freeways, it's very challenging to apply very speed limit. However, when we look into RAM metering, why we didn't get very high performance, we found that applying this is the regulator results. Applying each RAM in optimize the flow individually, we push more and more vehicles from upstream to downstream, ending up to very highly congested scenarios that might not be controlled. So we used this. We looked into each region individually. We found that upstream at early regions, like at third line up by brand regions, we can get very high performance from RAM metering, like 40%, 50%, and sometimes 50%, like in Erin Mills. However, we lose part of this benefits downstream when we go to Kaustra or Dixie region. We have uncontrolled scenario where vehicles are very high demand coming from upstream, so we can lose up to 77% and 65% increase in total travel time. So for RAM metering, we give priority to mainline demand, and for large network, we have significant benefit from upstream, which we push downstream that can increase the delays and have very challenging situation downstream. For very speed limit, when we have higher demand or very high congested scenarios, very speed limit alone is not enough, and it gives priority to RAM demand. However, we don't have space to store vehicles on the mainstream. Taking this results to design a RAM metering solution for QEW in collaboration with Xiaoyu, as it's discussed in the traffic signal. We adopted and extended from eMarvin for traffic signal. We design the controllers such that all upstream controllers looks at downstream RAMs and collaborate with them. So we take into consideration what is happening downstream because it's the most challenging part, and look at the local observation, state, and reward for our local. Each RAM meeting looks at its local reward as well as the two downstream RAMs at Kausra and Dixie, and emulate the same thing as the encoder and executor network for each one to deal with the amount of data arriving to each agent and optimize based on that. As a result, we applied that on the second half of the freeway, the second hotspot, which is more challenging to control, starting from Ford Drive till Dixie region. We can find that when we apply e-margin, we got decrease in total travel time, which reached 39% decrease in total travel time. And we can see clearly from the heat maps that we dissolved most of the congestion, and even the small amount of congestion that is not yet dissolved is still not very red as before. We have better speed profiles, and we can see clearly that the distribution of the benefits between RAMs is much more better than before. So looking into not only this is the travel time from the beginning of the freeway till Garnley Expressway from different regions. So this table reflects how good is the controller for freeway travelers. However, we have another side, which is the access time to the freeway. We looked into that to see what is the bad side of the controller or what's happening. We looked at all the access time from each region, and for every controller, we can find clearly that there is no increase in access time from one region to another. However, we found that there is a huge increase in access time from Horentario, which reaches 3.65 minutes at this RAM from at Horentario region. And when we look to that, we have in our simulation, we modeled the freeway and the parallel arterial, and which is the South Service Road, which is alternative to be traveled on. And we found that at Mississauga, between Mississauga Road and Horontario, we have the Credit River, which cuts the Sound Service Road. So the algorithm learned, or the reinforcement learning controller learned, that it can actually decrease the flow from the on-ramp so that it can push more vehicles to use the South Service Road at Horontario region, which is benefiting them. If we look at Horontario region, we will find that they are benefiting 10%. However, a small portion of vehicles are still using the freeway. This portion of vehicles are having the 3.6 waiting time before entering the freeway. Conclusions from this work: we have any control in any case better than none for QW or isolated RAMs. Whenever we apply control, it get some benefits. For RAM metering, it's better than a very speed limit in highly congested scenario. Reinforcement learning based controllers are based on any regulator based ones. We have significant benefits for coordinated RAM metering compared to isolated control. And we found, as we mentioned, the ability of eMarlin to learn how to decrease or increase the flow from each RAM to control the route choice of vehicles. So it tightened the demand at Horontario to make travelers take the South Service Road, which benefit everyone in the network. And ongoing work, we are applying eMarlin transformer to overcome any partial observability issue in our controlling and analyzing the controller's environment impact. And that's all for today. Thank you.
All right, thank you, Omar. We have some time for questions, if anyone has questions. There is a question. How were the heat maps generated?
Well, it's a question of how the method, or it's using the speeds on the freeway. So we measure the speeds each region using the detectors based on the freeway, and using these speeds, we produce the heat maps. So the heat maps, maximum speed is 120 and the minimum is zero. So when it's dark red, it's zero, and maximum, which is green, it's 120.
It's kind of like a Google map, but you're spreading it over space and time.
Yeah.
Any further questions?
Our speed reduction achieved in simulation. I'm not sure if I have to share my screen. Uh, so we have the speed reduction. Yeah, we can see that it's what's achievable in the simulation can be achievable in real time because we have calibrated demand, which reflects uh, traffic performance of real world. So if we have uh, decrease in total travel time or increase in speed, it can be achievable if we are having correctly calibrated simulation, which is, I think it's the case here. We have calibrated the network so that we reflect how the fundamental diagram or the relation between the driving behavior in Ontario on QW and what we have in the simulation. So
So I
whatever we
think
have in
if I understand the question correctly, he's asking um, how how do you get people to slow down? Is it a changeable message sign? Is it in the simulator? How do you
for
make
very speed
people
limit.
for variable speed limits? Yeah.
Yeah, for very speed limit, yeah, it's like a very message sign as a controlled section. So if we look at very speed limit at the network, we have here a controlled area. So we apply here very speed limit. We have a very message sign. But however, we didn't model for compliance rate. We model like when we put 30 kilometer per hour, everyone in this area will apply 30 kilometer per hour. We didn't uh, model how some people will not uh, comply to that. However, in literature, we have studies showing that if 30% of 40% of vehicles are controlled and complying to this speed limit, everyone will be stuck behind or they will not have a chance to overcome them.
So the answer, David, is that simply it's a dynamic speed sign that changes every 1 minute or so, displaying what the speed limit is in that section. In the future, you can also rely on connected vehicles where you broadcast the speeds directly to the vehicle to implement. But the most basic implementation is just a dynamic sign. Any more questions? If not, then thank you, Omar.
Yeah, we
And
have.
is there another one?
Yeah, I
Speed
think.
be can dynamic sign speeds be enforced? Yeah, sure. Like if there is a speed limit and you violate it, it can be enforced in so many ways. Cops can stop people and give them tickets, or if you
Yeah,
have radar enforcement, for instance. So the enforcement part is the implementation and the enforcement uh, are not difficult. Now, what people object politically, that's a different story. But in terms of executing the speed limit and enforcing it, technology is readily available.
yeah, just
I have
like
an,
how speed changes in at construction areas, for example, but it's variable message sign instead of, for example, it's enforced at construction areas. If speed falls from 100 to 80 or 70, it's enforced, and if you violate it, you will get ticketed most of the time. So I think it's the same thing, but instead of having dy static speed limit, it will be variable using any message sign or.
and we have a comment from Jack saying that motorways in Australia and Europe have a speed limit posted on LED screens beside the motorway, which was what we're talking about. And Australia, it seems they use automated speed cameras to enforce the variable speed limit. So, like again, the implementation is not the challenge. It's how they come up with a speed limit. That's what Omar talked about using reinforcement learning, and then how to deal with objections from the public that you're now putting speed limits on freeways, dynamic speed limits on freeways. That requires, of course, public education explaining that when you create controlled congestion, that's better off. Everybody's better off because you don't activate the bottleneck downstream. And if you don't activate the bottleneck downstream, you can have significant savings. But having said that, and as Omar explained, is if the freeway is packed, which is the case in many places during rush hour, and if the ramps are back to back, there isn't much space between the on-ramp, then we've seen that dynamic speed limits are not the best. And ramp metering is much, much more effective than dynamic speed limits. So that's why our recommendation is for our conditions here, the QW, for instance, during the peak of the peak, we recommend ramp metering and we caution against dynamic speed limits because it's not as effective. Okay. So thank you, Omar. We move on to the next presenter. The next presentation we have is from Dr. Karim Osman. He is also a postdoctoral fellow at U of T at the Transit Analytics Lab. And his research, he finished his PhD under the supervision of Professor Amr Shalabi and myself. And his research interests include public transit, electric buses, multimodal corridors. Multimodal here means vehicles and transit, traffic management, and intelligent transportation systems. So with that, Karim, I turn it over to you. Please go ahead.
Can you see my screen?
Yes, we do.
Okay. So good morning, everyone. Today I will give a presentation about the multimodal adaptive traffic signal control we have developed, and we have used reinforcement learning. So you should be familiar with reinforcement learning by now, given the previous two presentations. So it shouldn't really be, we have been using basically the same framework that's used by Omar and Xiaoyu. So I'll just basically start with the issue of the current transit system. Transit is actually frequently or commonly characterized as a slow service. And when you look at the history of public transit, you will see that the current transit speed is not really faster than how it was a century ago. So basically, we have almost the same average traveling speed. And when transit is competing with other modes, you will find that transit is actually in disadvantage. For example, when we compare transit to driving, you will find out that the average traveling speed is actually significantly higher than the average transit speed. And in some scenarios, you will find that even cycling is faster than using public transit. So what is the meaning of slow transit service? It means higher operating costs for transit agencies and customer dissatisfaction. And in that case, people will start looking for other modes to shift. They might actually prefer cycling, they might prefer driving, and they might shift from using public transit to other modes. So what are the main sources of transit delays? We have intersection delays, including traffic signals, and we have link delays. And for our work here, we will focus on intersection delays. And when we look at dense urban areas, we will see that around 35% of the transit travel time is actually spent at the intersections, actually highlighting the importance really of dealing with intersection delays. And traditionally, there is the transit signal priority. So traditionally, transit signal priority will be implemented to prioritize transit at the intersection. However, the main issue here is that you prioritize transit on the cost of traffic, And on the other hand, you will see that there is the adaptive traffic signal control, but adaptive traffic signal controls are mainly optimized based on traffic demands. And what about buses? They don't really look at what happens to transit. And on the other side, you have the transit signal priority that doesn't really consider traffic. And again, we will get back to the same picture, either to prioritize transit on the cost of traffic, or you do nothing, and then you will have slow transit service. So there is no strategy that actually adaptively reduce the delays for both. So our main objective in this work was really to provide a multimodal adaptive traffic signal control for everyone, basically for transit and for traffic. So we have been using reinforcement learning. I know that you should be familiar with reinforcement learning by now. I'll just go over it very quickly. So reinforcement learning is pretty much similar to a PAPI. It actually mimics the way a human child really learns, and it involves trial and error in order to achieve certain goals. And basically, reinforcement learning is like a child. It learns by interacting with the surrounding world, and it learns over time. So basically, this is a very famous reinforcement learning figure. You have your agent taking action, changing the environment, and based on the changes in the environment, the agent will receive a reward and will receive the new state of the system. Right. So there is a lot of examples for the applications of reinforcement learning. This is one, and I will not really open the video now, but it has been used for a lot of applications, hide and seek games. On Earth, the simple rules of... Right. Yeah, it has been used for parking cars, and as you have seen in the previous two presentations, it has been used for traffic signal control and for ramp metering. So we have been using it for our problem here. And again, this is the same simulation network that Xiaoyu has presented. This is the Yang and Steels intersection. And our main goal here is to actually provide a multimodal adaptive traffic signal control to actually optimize the conditions for both transit and traffic. And in our simulation here, our agent is the traffic signal controller, and it takes an action regarding the traffic signal, which direction to give the green phase and for how long. And it interacts and it changes the environment. And in our case here, the environment is actually our simulation model. And based on the changes, again, it's received, the agent will receive the reward value and the new state of the system. So let's look at our simulation area from public transit perspective. So our simulation area is actually in the boundaries of the TTC and York Region transit service areas. And this is actually a screenshot from the TTC website showing the transit routes that actually use the simulation area. And we can see that we have 4 high-frequency TTC bus routes. And you can see the numbers, bus route 60, 53, 960, and 953. And when we look at what's happening at York Region, basically, French-Go is actually one of the main hubs for York Region transit. And basically, most of the transit routes are actually passing through our simulation area. This is actually the Yang and Steele intersection here. And we have 16 York Region transit routes actually using our simulation area. They are actually having high and low frequency. So when you look at the combined headway, so the TTC combined headway is actually 1.9 minutes, and the combined frequency is around 31 buses per hour. And for York Region, the combined headway for all the routes is around 1.8 minutes. And it actually shows the number of buses that actually use the simulation area in 1 hour. So the combined frequency is actually around 65 buses per hour. So you have around 65 buses per hour trying to use your simulation area. And actually, it's not really possible to deal or handle an intersection similar to this with no TSP or with using the traditional TSP, because basically or usually the traditional TSP systems are ignoring or actually considering only the first request and ignoring the remaining buses entering in one cycle. Anyway, we have used the eMarlin multimodal system, and again, this is the same hierarchy or the same framework that both Xiaoyu and Omar have shown in their presentation, so I will not really get into the details. This is the eMarlin framework. And we have tested two adaptive traffic signal control systems. One is vehicle-based, and in the vehicle-based, the main objective is actually to minimize the vehicle delays. It doesn't really consider transit. So basically, in this scenario, a bus with 50 passengers on it is similar or will be dealt with similar to a passenger vehicle with one passenger one passenger on board. On the other hand, we will have the person-based reward, which actually tries to minimize the person delay. And this system or this model is actually trying to take the vehicle occupancy into consideration. All right, let's look at the results. So basically, this is the results of the vehicle delay system. So our benchmark is the pre-timed signal control system, and we can see that the vehicle-based is actually achieving the lowest vehicle delays, and on the other hand, the person-based RL is actually achieving slightly higher vehicle delays. But what we really care about is the person delay. You are trying to minimize the overall person delay in your system. So as we see here, we will see the opposites happening. So your person-based reinforcement learning adaptive traffic signal control is achieving around negative 55% or 55% reduction in the person delays. And this is actually higher than what was achieved using the vehicle-based reinforcement learning. All right, then we tried to test the efficiency of these two systems, the vehicle-based and person-based, at different levels of bus occupancy. And in this figure, we are showing the vehicle delay moving on the x-axis. We have the bus occupancy from low occupancy to intermediate to high occupancy, and on the y-axis we have the percentage of a change in the total vehicle delay. This is in comparison to the base case or the benchmark, which is the pre-timed traffic signals. And we will see that at the beginning, at low bus occupancy levels, both the vehicle-based and person-based are achieving basically the same results. But with the increase in the level of bus occupancy, you will see that the vehicle-based is not really affected, because it's just trying to minimize the overall vehicle delays, so it doesn't really get affected by the bus occupancy. But on the other hand, the efficiency of the person base is actually decreasing with the increase in the vehicle occupancy. But again, this is not what we really care about. What we really care about is to minimize the person delay. And again, this is the same figure, but for person delays for the two methods, the eMarlin person-based and the eMarlin vehicle-based. And let's look at the vehicle-based. So basically, for the vehicle-based reinforcement learning shown in green here, you will find out that the efficiency of vehicle-based methods is actually decreasing with the increase in the bus occupancy. Again, because this method is blind to the level of bus occupancy, it just optimizes for vehicle delays. But on the other hand, you will have the person-based method is actually increasing the efficiency of the system with the increase in the bus occupancy, because you are taking the level of occupancy into consideration, and the level of occupancy is actually part of the optimization problem. So this is actually showing us that the person-based methods can automatically adapt to different scenarios, and we can see that when compared to the vehicle-based method, person-based is actually superior, especially at intermediate and high occupancy levels, and it actually offers adaptive priority. So basically, the final conclusions of this work, we have seen that eMarlin, basically the person-based eMarlin, can achieve significant reductions in person delays, around 55% reductions. And at low bus occupancy rates, both the vehicle-based and person-based methods converge and achieve basically the same results. And finally, we have person-based methods can actually adapt to the level of bus occupancy, and it can actually tackle the trade-off between traffic and transit. And in other words, it actually resolves the conflict between TSB and the traditional adaptive traffic signal controls that only consider traffic into the optimization problem. And that concludes my presentation. Please feel free to ask questions.
Okay, thank you, Karim. We're actually a bit ahead of time, so we can entertain questions. Either put them in the chat box or raise your hand, I guess. Okay. I am not seeing questions.
Yeah, I think
Brendan, Emily, um, go ahead.
Hi, very interesting. Just curious, what would be required to deploy this the person-based adaptive integrated adaptive control? I would gather at the very least you would have to have real-time information about passenger loads, which does not exist now. But are there other requirements that would be needed?
yeah. So basically, we'll need a number of data sets. And for the level of occupancy, we currently have the APC, the automated passenger counters. We can rely on that as a source of data for the number of or bus occupancy or the number of passengers on board. So actually, this is one of the data sets we need. But in terms of traffic, we need some information about the speeds of the vehicles, about the number of the vehicles. But we can really use cameras to detect this information. It can actually classify vehicles. You can know how many vehicles, how many buses at the intersection area. You can get information about the speeds. Um,
हो गया था तो आया क्यों
So,
नहीं?
so, so I think the detection for traffic
हुआ
is the
कौन
same as
कॉल
any
करेगा?
adaptive traffic signal control system. Most likely cameras, but you can use other methods as Xiaoyu indicated in his presentation. But I think this question is focused on what do you need from transit? So we need the number of passengers on board with automatic passenger counters. The TTC, we presented this to the TTC, they have them on some of the buses. So the technology itself exists. But my understanding is that this is not communicated in real time um, for real-time control. This is communicated every few minutes. Don't quote me on that. But I think what needs to be done is to enable the communication of the number of passengers in real time to the traffic signal control cabinet.
Right.
Now, what if you don't have it? Then in this case, you could assume a number. So for instance, during the peak period, you could say the average bus occupancy on this corridor is X, like 30 passengers, for instance, per bus. So every bus that will show up will be weighted or like a weight is assigned to it, which is 30, which is the number of passengers, assumed number of passengers on the bus. You have to vary that, for instance, like during off-peak or during nighttime, then you would use a lower number. So let's say, for instance, at midnight or 11 p.m., your average bus occupancy is 5 or 10, then you use that. So that's like an approximation of the number of passengers on the bus in case you don't have APCs. Of course, this system is intended to have APCs, but can also function with reasonable assumptions.
Right.
Um,
Using historical data is fine as an approximation, like you said. I'm just was asking because APCs, most of them, I'm not absolutely sure about the current TTC one, but APC data is downloaded at the end of the day and processed as an archived data. It's not done in real time. During COVID, a couple of transit systems did have real-time loads, but it was a very crude approximation just to tell people how crowded the bus was. But it was sort of like three levels, green, yellow, red, and not very many transit agencies even had that. But it's feasible to do it if you've got the bandwidth. So
exactly. So yeah, the technology is there. It's just a matter of configuring it to work in real time.
yeah.
But one interesting question I had about this is that even if a bus is empty or near empty, um, we still need to push that bus because there are people waiting for it downstream. That's a tougher one to crack because now you need to know how many people are waiting downstream. So that requires, if we want to do it correctly, requires that we also have uh, some method of detection to detect how many people are waiting at the next bus stop and take that into consideration. So if a bus is approaching an intersection, it is near empty, but I know that 20 people are waiting put it in the next bus stop or two, then you can still wait that bus with 20, taking into consideration what is waiting for that bus to arrive early. So that's another possibility. Or again, let's say, for instance, you want to do like brute force transit priority at this intersection, then you can just assume that all buses have people on them, and that will be taken into consideration in the optimization. How different is that from just TSP? Well, TSP, first of all, deals with the first bus, and then ignores everything else. It doesn't take into consideration impact on traffic, so it's not optimizing for the whole system. And if you have an intersection like this with less than a minute headway from all directions, it's impossible to apply conventional TSP. So I'm kind of going back to the comments here. I have a bunch now. So Michael Roshlow says, does this mean you need dynamic data on how many people are in each bus? Yes, I think we have already addressed that. Question from Kareem Salama. How the network scale can contribute to affect the optimization approach and result, or does that matter much? So if I understand the question correctly, I think you're asking about like at the time of deciding for a given intersection, are we taking into consideration the rest of the network? Our research has shown that what impacts the decision making at the current time, like you need one hub information from the upstream, meaning that ideally that intersection needs to know just one intersection upstream, what is coming from the one intersection upstream, as Xiaoyu explained in his presentation. Further upstream doesn't really impact the decision of a current intersection. Like if you have, for instance, a tension mechanism, you'll find that the attention to the upstream intersection gives you 95% of the data that you care about. That's for deciding at a given intersection. Now, there's a totally different level if you're talking about cordon control or perimeter control. That's a different ball game we're not talking about today, where, for instance, like the whole downtown, for instance, is surrounded with a corridor and control vehicles in and out of that corridor with traffic light. That's a different scale problem that we haven't addressed today. But ideally, you want to have a regional control mechanism and then local control mechanism. So everything we talked about today is localized. Michael Roshlow again, but TTC apps are already showing routing in real time. Yes, we talked about that. Jack, TTC still does the 3 level of loading on buses reported in the LPS. David Chen, can you use historical data to predict the number of people at the bus on the bus and waiting for the bus? Yes, we can. Michael Roshlow, another issue is that the transit vehicles should always be given priority regardless of occupancy. So we talked about that as well in terms of the policy might, TTC, for instance, might wish to push all buses taking into consideration what is waiting for them upstream. I think we touched upon all these questions. Anyone wishes to ask further questions? I guess not. So thank you very much, Kareem. We move on to the last but not least presenter. Kareem, if you stop sharing, please. Thank you. The fourth presenter is Tianyu Shi. He is a fourth-year PhD student at the University of Toronto, working under my supervision. Um, his main research focus is again using reinforcement learning control, but he focuses on automated driving. So, in other words, coming up with car following and lane changing models um, that control the vehicle driving process, not the infrastructure level control, meaning that is not using ramp metering, for instance, or dynamic speed limits at the infrastructure level, but is microscopically focused on um, operating a vehicle. On the personal side, he loves playing basketball and swimming. So, Tiani, you with this introduction, please go ahead.
Thanks for your introduction. Can you could you see my slides and hear my?
Yes,
Okay. Thank.
yes.
So today I will present Sequem, safe, efficient, comfortable autonomous driving model with reinforcement learning. This work is in collaboration with Omar, Lydia, and supervised by Professor Bahar. So today we will introduce from the uh from the one-dimensional Sequem to two-dimensional Sequem model, and we will also briefly touch the on my ongoing work on the cooperative version of the Sequem 2D model. So firstly, the background is the congestion on freeways is a, a worldwide problem. It costs uh many dollars every year and make the traffic condition getting worse. So unlike previous presenter like Almer's work, we in this work we mainly focus on the microscopic part, how we use the CAV model to address the traffic congestion problem. So firstly, we will talk about the microscopic versus macroscopic. From the microscopic, we mainly use the CV model to for control. So in this problem, we have the leader vehicle and follower vehicle, and we try to optimize the uh, s- autonomous driving vehicles behavior to improve, for example, the micro efficiency such as headway speed and improve safety. Uh, so the overall result, we want to develop a CV model that can achieve the same effect as you control the infrastructure level size. For example, we also want to, from the macro level part, we want to maximize the throughput, mitigate the total travel time. So this is the main focus of this of my research. Mm, uh, in my in my research, I did several literature review. We find that in previous literature, most RL car following model they just mimic human driving behavior. They are not the best performance in terms of efficiency. Also, they don't have the speed limit as a target in their car following mode. They neglect the dependence on both leading and following vehicle. So that means they have a unilateral view. So in this work, we try to develop a model that can maximize efficiency and follow speed limits. Most importantly, we also want to guarantee safety, and also we want to maximize the comfort of the model. So based on so in other words, we want to develop a model that can better perform than previous existing human-like driving model. And furthermore, we want to extend the model from one-dimensional to one-dimensional means car following behavior to two-dimensional with lane changing, and we also want to provide safety guarantees. This is what we refer to the Sequem 2D model. Um, Firstly, we will introduce the concept of our Sequem model. We know headway significantly impacts traffic performance. It will impact the efficiency. For example, a smaller gap leads to higher road flow. Also, it will impact the safety. A large enough gap will avoid unsafe situations. So we know this is a trade-off between safety and efficiency. So next, the question is how we can deal with those conflicting goals. So we want to formulate uh target target gap that can guarantee safety by to make the follower stop safely if the leaders apply emergent braking. Uh, Furthermore, we want to maximize the efficiency and make sure this is a minimum safe gap. So in this formulation, we can formulate a variable target gap. So uh, this is a concept of our sequence model. Uh, we we propose that uh, no target gap setting that is always optimal. A given gap will either be inefficient or unsafe. So our model, we want to formulate a target gap that can guarantee safety will maximize the efficiency. So also in our experiment, we find that learning target speed is simpler than learning target gap. So we transform the formulated target gap into the target following speed. So so that we have the sequence model. When we have the sequence model, next question is how we can train the model to learn the behavior we want. So we use reinforcement learning. I think you guys already uh, get familiar with reinforcement learning, and we have the agent. The agent is the autonomous driving vehicle. So in this experiment, we also can give the autonomous driving vehicle the information such as vehicle speed, relative speed, speed limits, spacing, and the acceleration information. Uh, in the one-dimensional sequence model, we aim to control the longitudinal acceleration, deceleration of the model. In other words, it is a conforming model. So the reward is the linear combination of those two components, both speed and comfort. So we formulate the target speed as one of in the speed function objective. We also formulate the target. We also formulate the comfort as another function to penalize jerk. So we can use reinforcement learning to optimize those objectives to make the model drive safe, efficient, and comfort. We construct the several experiments to validate our model's performance. We consider the ring shape network and we compare with several human-like driving models. We also compare some models from literature using reinforcement learning models. So we can find that our model can perform better in terms of the average time gap and average jerk. So that means our model can improve the efficiency and comfort. To further validate the safety, we perform another experiment with leader vehicle to take an emergent brake. We we use the same environment and we measure when leader vehicle take emergent brake, how our model can react, and we can see our model can react safely and without crashing. And meanwhile, we can have the lower jerk and lower time gap. So uh, this is the result of the model in terms of normal driving and emergent braking. So next question, we aim to investigate how we can extend the driving model to a two-dimensional driving model by considering the lane change behavior. So in terms of lane change behavior, we uh, inspired from the one-dimensional model. We formulate the target speed as two-dimensional, so we can make the vehicle to conduct the line change. So take this graph as an example. Consider we have multiple lanes. So by extending it to two-dimensional, we aim to let the ego driving model can follow a leader with higher target speed. So we did several literature reviews. We found that in previous literature, either they cannot guarantee safety, or they uh, cannot extend to two-dimensional model. So in this work, we try to fill those research gaps. So to improve the training efficiency, we construct a RAIN network with multiple lanes. So this is a training environment, and we have the autonomous driving vehicle as the red vehicle, and we have the human driving vehicle as the yellow vehicle. And we train the model in the ring-shaped network, and we also evaluate the model in several different settings, such as normal driving, emergent brake scenario. Also, we try to improve the traffic density to make the scenario to be more challenge. And we compare the model with several base sets, and it demonstrates better performance. So uh, so in this model, to be more specific, we construct the privacy environment as we see in this slides, and we also force the constraints. Unlike the one-dimensional model, we develop the line change constraints that can guarantee safety in the two-dimensional environment. So we have the safe gap to left lane, right lane, and eagle lane. We also so this constraint force like a shield. So this can uh filter out to forbid the unsafe actions so that we can make our model to drive safely. Uh, Also in this reward function design, uh, since we want the model to conduct the line change, so we considered both discretionary line change and mandatory line change. For discretionary line change, it's easy to understand is when the model drive in the highway, it want to improve the efficiency, so it has to make the line change. For mandatory line change, it means if the model want to switch to another route, so it has to make the line change. So if it cannot make the line change, it will receive penalty. So this is the concept of mandatory line change. So we want to build a full driving model that can drive safely, efficiently in all the networks. So uh, to validate the performance, we compare the model in both synthetic network and real network. So like the QEW network from previous literature. So we compare uh traffic uh different traffic conditions from very compact traffic to from very high density traffic to low density traffic. We also compare the emergent brake scenario and we compare the merging scenario to show how our model can perform in those scenarios, how we can handle those complex scenarios. And we can see our model can achieve the zero crash rate and also in most conditions, we have the highest efficiency and best comfort. Mm. So this is the work of the Sequem 2D model. Now we have a full driving model. Uh, However, we also think about that model. For this model, we think it's mainly focused on the ego driving behavior. So that means it's try to maximize the driving performance of the ego vehicle, like the safety, efficiency, comfort of the ego vehicle. Uh, our whole picture is trying to improve. We can go back to this slide. Our whole picture is trying to improve the macro efficiency and improve the traffic. So how we can achieve these goals? So we are currently building the cooperative version of the Sequem 2D model. So that means within the we call the scan range within or collaboration range. Within the collaboration range, we aim to uh motivate them to collaborate with each other and to improve the group behavior, and so we can improve the whole traffic performance. We consider uh, n number of agents in its neighborhood, and we modify the reward function to consider their impact, and we aim to motivate the vehicle to collaborate with each other in order to uh, improve the system performance. So this is ongoing research of the Sequem 2D model. Thanks for your listening. Do you feel free to ask me questions. Thank you.
All right, thank you, Tianyu. If you have any questions, please raise your hand or type in the uh, chat box. Okay, so I guess there are no questions. Yeah, Tianyu, could you go back to the slide where you showed crashes of other models? I think you went quickly over that. Maybe it was not clear.
Uh, do you mean here?
There was a slide earlier about the Seacrem model and testing under
Oh,
regular driving,
oh,
emergency braking, and
yes,
uh,
here.
so can you just like slowly explain that again? What happened with those crashes?
Uh, so in this case, we consider uh, there's a leader vehicle and there's a follower vehicle, and we consider the same leader vehicle for all the baselines, and the leader vehicle will take an emergent brake. So the follower vehicle needs to react in response to this emergent break. And a good model that can guarantee safety is they can handle the emergent break situation without crashing. And so from the result, we can see on the on the left. So we know firstly we know different time gap will result in different behavior. So for fair comparison, we firstly construct the left part experiment. We use the same time gap for all the model and same time gap as our sequence every time gap sequence target time gap. So we find that with the help of our formulated sequence constraints, our model can avoid crash, and our model can have the least jerk compared to Gibbs model. Gibbs model is similar formulation as our model, so that it could affect the crash rate. It could also handle this case. However, we see the Gibbs model, they didn't optimize the comfort, so that's why they have a higher jerk. On the other hand, if from the right table, if we have different time gap, so logically those model like IDM, Shadoover, they have a higher target time gap. So we can see based on their smallest safe time gap, they can avoid crash. However, their efficiency is greatly sacrificed. So we can see from the right table, it has much higher time gap compared to sequence model. So that we can validate in terms of safety, the sequence model can guarantee safety in the extreme case. And in terms of other criteria like comfort, we also can have better comfort compared to other baselines. So this is the experiment we try to show. Yeah.
Okay, so I think he glanced over it quickly. So let me recap. Just tell me if I got it right. So the right-hand table shows that if all models try to drive safely, some models, for instance, like IDM, will maintain 3-second headway, which is very inefficient. So that's detrimental to freeway capacity, for instance. While the sequence model achieves the lowest headway of about 0.57 seconds or so. But all of them are safe, and they vary in how efficient and how jerky the driving is. Now, if we take the sequence performance, which is 0.57 or 0.58 headway, and tell all the other models you have to try to give us the shortest headway like that, which is your target now is 0.6, then they crash as in the left table, correct?
Yes, that's correct. Yes.
All right. Any other questions from anyone? So I think, thank you, Tinyu. I think we're perfectly on time. Now we'll take a 15-minute break and we'll resume again at 11 o'clock sharp. We'll start with the second session on behavioral modeling in the context of emerging mobility. And Dr. Karim Osman will moderate the session. Thank you and see you at 11.